Good evening to everyone. I am Dr. Rajini Samuel, Professor of Biochemistry, Shri Sathya Medical College and Research Institute, SBV Chennai Campus, Tamil Nadu, India. First of all, I thank the organizing committee of AVER Conferences for inviting me to speak on my research topic, Unlocking the ABG Results Using Novel Acid-Base Balance Theory in the World Congress on Cardiology and Cardiac Diseases. Specific learning objectives: to discuss the role of ABG in myocardial infarction, to construct a novel four-quadrant graphical tool for ABG interpretation to represent various acid-base disturbances, to develop a novel ABG interpretation method using changes in pH, to apply a newer equation that helps in better understanding of the concept of hidden acid-base disorders, to identify the mixed acid-base disorders, to create a 7-step for ABG interpretation integrating various approaches. Myocardial infarction and ABG. The most common cause of cardiovascular disease mortality worldwide is acute myocardial infarction. Arterial blood gas analysis plays a significant role for evaluating the clinical course and management of acute myocardial infarction. According to the European Heart Failure Guidelines, in acute heart failure patients, blood pH, partial pressure of carbon dioxide, and lactate levels should be measured. Among acute myocardial infarction patients, heart failure is the most powerful predictor of death. Acid-base disorders in MI. The most common presentation of acute heart failure is dyspnea, and ABG analysis has immense clinical value in decision-making process for most dyspneic patients. The most common abnormality seen is metabolic acidosis, followed by respiratory alkalosis. Metabolic acidosis could contribute to the development of cardiac arrhythmias. The definite correlation was found between metabolic acidosis and mortality. Lactate and base excess may serve as a prognostic marker. Hyperventilation is commonly seen in pulmonary edema, but hypoventilation have been reported in pulmonary edema due to considerable mechanical restriction on the lungs in severe cases. Patients with chronic diuretics are more likely to have metabolic alkalosis. ABG interpretation remains an arduous task, yet it has immense clinical value in saving the life of the cardiac patients. Various approaches in arterial blood gas. The various approaches are physiological approach, base excess approach, and physicochemical approach by Fensley-Stewart. The most commonly used approach for arterial blood gas interpretation is physiological approach, which is based on the bicarbonate carbon dioxide buffer system. pH is equal to pKa plus log of bicarbonate divided by carbonic acid. Most blood gas analysis uses the Henderson-Hasselbalch equation to calculate bicarbonate values. Bicarbonate concentration is a variable parameter because it varies with the changes in PCO2 values. As PCO2 increases, it reacts with water molecules to form carbonic acid, which dissociates into hydrogen and bicarbonate ions. Concentration of bicarbonate increases with increase in PCO2 and decreases with decrease in PCO2 values. This problem of respiratory influence in causing alterations in bicarbonate concentration is solved by the measurement of standard bicarbonate. Standard bicarbonate is the concentration of bicarbonate in plasma from blood, which is equilibrated with a normal PCO2 40 mmHg and a normal PO2 over 100 mmHg at a normal temperature 37 degrees Celsius. The actual bicarbonate and standard bicarbonate concentrations are approximately equal under normal ventilation, but in hypoventilation and in hyperventilation, the two values differ and deviate from each other. So the novel ratios are derived. Ratio 1 is equal to ratio between bicarbonate and standard bicarbonate, and ratio 2 is equal to bicarbonate minus standard bicarbonate divided by carbonic acid. So two graphs are plotted. In the first graph, in the x-axis, PCO2 is taken, and the y-axis ratio 1 is taken, the ratio between bicarbonate and standard bicarbonate. In the second graph, in the y-axis, ratio 2 is taken. At PCO2 of 40 mm of mercury, both bicarbonate and standard bicarbonate values are equal. So the difference is 0. The ratio 2 is 0. Similarly, the ratio 1 value is 1 at PCO2 of 40. So another ratio, modified ratio 2, is equal to standard bicarbonate divided by 1.2 minus bicarbonate divided by carbonic acid. So standard bicarbonate is calculated at PCO2 of 40. So at PCO2 of 40, the carbonic acid concentration is 1.2. So the ratio 2 is modified. So it seems logical to correlate with standard bicarbonate with carbonic acid concentration 1.2. So you can compare the two graphs. In the first graph, PCO2 and ratio 2 is taken, and the second graph PCO2 and modified ratios to be taken. So in the modified ratio 2 clearly demarcates the different PCO2 values. So obviously the value of ratio 2 is 0 if the ratio 1 value is 1. Both the ratios ratio 2 and modified ratio 2 are greater positive for increased PCO2 and greater negative for decreased PCO2. The advantage of modified ratio 2 is that it clearly demarcates different PCO2 values. These ratios are greatly altered in respiratory disorders and also in metabolic acid-base disturbances associated with respiratory compensations. So these novel ratios render some clues in discriminating various acid-base disturbances. So novel 4-quadrant graphical tube is constructed using standard base excess in the x-axis and either modified ratio 2 or PCO2 minus 40 in the y-axis. So each acid-base disorder will occupy any of the 4 quadrants. The normal report will be seen around the center of the graph. The normal reference range for standard base excess from minus 2 to plus 2 millimole per liter. The normal reference range for PCO2 is from 35 to 45 mm of mercury, and PCO2 minus 40 is from minus 5 to plus 5 mm of Hg. So once the major primary acid-base disorder is identified, the compensation rules will guide to identify the second primary acid-base disorder. So PCO2 minus expected PCO2, if the value is greater positive, then it denotes presence of respiratory acidosis. If it is greater negative, it denotes the presence of respiratory alkalosis. If there is difference is within acceptable limits, then it denotes no second acid-base disorder because it is due to compensations. Similarly, the bicarbonate minus expected bicarbonate, it is greater positive, it denotes metabolic alkalosis, greater negative, it denotes metabolic acidosis, and the difference is within certain acceptable limits, it denotes only compensations and no second acid-base disorder. So these are the 6 bicarbonate-based bedside rules for acute respiratory, chronic respiratory acidosis, acute respiratory alkalosis, and chronic respiratory alkalosis, and rules for metabolic acidosis and metabolic alkalosis. So acute and chronic is only for respiratory acid-base disorders and not for metabolic acid-base disorders. The 4-quadrant graphical tube is constructed. In the x-axis, standard base excess is taken. So in the first quadrant, the point is toward the first quadrant. Towards the x-axis denotes metabolic alkalosis. Similarly, the point is towards the negative side of the x-axis, it denotes metabolic acidosis. The plotted point is towards the positive side of y-axis, it denotes respiratory acidosis. And if the plotted point is towards the negative side of y-axis, it denotes respiratory alkalosis. So after applying the compensation rules, if the shift is upward positive shift, it denotes additional presence of respiratory acidosis. If it is downward negative shift, it denotes additional presence of respiratory alkalosis. If it is right positive shift, it denotes metabolic alkalosis. And if it is left negative shift, it denotes metabolic acidosis. If no shift, it denotes only compensation and no second acid-base disorders. So these are applied after applying the compensation rules. So I have taken 232 cases. Different groups are formed using the different pH, PCO2 and bicarbonate values. So it's a graphical tube can be constructed using standard base excess in the x-axis and modified ratio 2 in the y-axis. So 4 quadrant, each acid-base disorder will occupy one of the 4 quadrants. Similarly, with PCO2 minus 40, another graphical tube constructed. These two graphs can be merged in 3-dimensional. So if suppose the point is in between, then it can denote either compensation or mixed acid-base disorders. So just by looking the plotted point in the 4 quadrant, it will be easy for us to identify the acid-base disorder. So non-respiratory hydrogen concentration. So modified Anderson-Isabelle equation, H plus is equal to 24 into PCO divided by bicarbonate. So pH is equal to 9 minus log of H plus. So the calculated hydrogen concentration equivalent of standard bicarbonate is called the non-respiratory hydrogen concentration. So the same equation, in the place of PCO2, you have to substitute 40. In the place of bicarbonate, you have to substitute standard bicarbonate. If you substitute, you will be getting NRH plus, non-respiratory hydrogen concentration is equal to 960 divided by standard bicarbonate. And non-respiratory pH is equal to 9 minus log of NRH plus. So graph is constructed. The relation between standard bicarbonate and NRH plus is clearly shown. So both are inversely related, and pH and standard bicarbonate are directly related. So using this concept, a novel acid-base balance series proposed. The net changes in pH of the blood reflects the sum total changes in hydrogen concentration of blood. The sum total changes in hydrogen concentration in the blood includes both the changes due to respiratory and non-respiratory component. So for this hydrogen concentration pH 7.4, which denotes homeostatic set point of acid-base balance. So the total change delta H plus is equal to delta RH plus delta NRH plus. Similarly, it can be applied for the pH change. The net changes in total actual pH is due to both the changes in respiratory and non-respiratory component affecting the pH. So delta pH is equal to delta RPH plus delta NRPH. So delta pH is equal to pH minus 7.4, and delta NRPH is NRPH minus 7.4. It denotes the non-respiratory component, and delta RPH is equal to pH minus NRPH, that is the respiratory component. So examples I have shown. So pH is 7.31. So delta pH is equal to pH minus 7.4. So minus 0.09. So delta RPH can be calculated using the formula. So if you add both delta RPH and delta NRPH, we will be getting the total change in pH. So in the second example 7.4, the delta pH is 0 because both the delta RPH and delta NRPH both are equal in magnitude, but the sign is different. So the total is 0. The third example 7.55, the delta pH is 0.15, delta RPH is 0.231, and delta NRPH is equal to minus 0.081. It is negative. So delta NRPH is equal to NRPH minus 7.4. The magnitude and direction, positive or negative of the changes in parameter, denote the metabolic component in causing changes in pH. Similarly, applies for delta RPH. The magnitude and direction, either positive or negative of the changes in the parameter delta RPH, denote the respiratory influence in causing changes in pH. So both the component values are more negative for acidic effect and more positive for alkaline effect. So relation between standard base excess and NRPH is shown. So standard base excess is a metabolic component. It is increased in metabolic alkalosis and decreased in metabolic acidosis, negative in metabolic acidosis. So NRPH is higher value in the standard base excess is more negative, and NRPH is less value, the standard base excess is more positive. Similarly, standard base excess versus the NRPH minus 7.4, the delta NRPH is plotted. Standard base excess positive and delta NRPH is also positive in metabolic alkalosis, and standard base excess and delta NRPH both are negative for metabolic acidosis. These are tabulated. Standard base excess more negative or base deficit in metabolic acidosis and more positive for metabolic alkalosis. A non-respiratory concentration is very high in metabolic acidosis and low in metabolic alkalosis. And NRPH is low in metabolic acidosis and high in metabolic alkalosis. So this is different from the normal pH. This denotes only the non-respiratory component. The respiratory component delta RPH, if you substitute the relation between pH and NRPH, we will be getting the relation pH minus NRPH. That is the delta RPH is equal to 1.6 plus log of bicarbonate divided by standard bicarbonate divided by PCO2. So if you this value is 0 at PCO2 40, and it is negative for increased PCO2 and positive for decreased PCO2. So it is clearly shown in the graph. If you look on the left, at PCO2 40, value is 0, and then for increased PCO2, the value is negative, and for decreased PCO2, the value is positive. So using this concept, a new interpretation method is developed. The normal reference range of pH is from 7.35 to 7.45. So delta pH will be from minus 0.05 to plus 0.05. If the value is less than minus 0.05, denotes acidic pH, and if it is more than 0.05 positive, it denotes alkaline pH. So delta pH is equal to delta RPH plus delta NRPH. So we can compare the delta pH with individual values. So delta RPH is more negative for respiratory acidosis and more positive for respiratory alkalosis. Similarly, delta NRPH is more negative for metabolic acidosis and more positive for metabolic alkalosis. So both the components are involved. It can denote either compensating mechanisms or mixed acid-base disorders. The changes in pH due to metabolic and respiratory component are equal but opposite. The net change will be zero because it is cancelled out each other. First, you have to identify the component that directly correlates with the delta pH in magnitude direction. So you have to see the sign, whether it is positive or negative sign. It will denote the first primary acid-base disorder. Then the changes in the other component is either due to secondary to compensations or second primary acid-base disorder. See, this can be easily identified using the compensation rules. If the expected level in the PCO2 or bicarbonate, then it denotes due to compensations. If the level is unexpected, then it denotes mixed acid-base disorder. So in this example, few examples are shown. So for the normal case, the first example you can look at pH is 7.37. The delta pH minus 7.4 is minus 0.03. So that is equal to both the total of delta RPH and delta NRPH. Similarly, we can apply for all the ABG cases. So you can go to the mixed cases, 7.12 pH. The pH changes, pH minus 7.4 is minus 0.28. So delta RPH and delta N both are negative. Both are contributing to the negative change in pH. So it is mixed. And second exam 7.42, the change in pH is 0.02. Delta RPH is positive 0.118 and delta NRPH is negative minus 0.098. So both are contributing to change in pH, but the respiratory is contributing in positive. So it is more positive for respiratory alkalosis and delta NRPH is negative. So more negative for metabolic acidosis. Both metabolic acidosis and respiratory alkalosis both are contributing to the change in pH. So this is for the metabolic acidosis. So pH, PCO2, expected PCO2 and PCO2 minus expected PCO2, bicarbonate, standard base excess and the novel interpretation all are compared in the same tabular column. If the expected values are there, then it denotes changes due to compensations. If the value is unexpected, then it denotes the presence of additional second acid-base disorder. Similarly, you can apply for the metabolic alkalosis also. So next one, I have applied for the respiratory acid-base disorders. So only for respiratory we have acute and chronic conditions. So if the value is expected, it denotes changes due to compensations. If it is unexpected, the difference between bicarbonate and expected bicarbonate unexpected, then it denotes changes due to second acid-base disorders. So we can compare the total change in pH with the delta RPH and delta NRPH. So we can say similarly a 4-quadrant graph can be constructed using delta NRPH in the x-axis and delta RPH in the y-axis. So 4 quadrants, the metabolic alkalosis, metabolic acidosis, respiratory acidosis and respiratory alkalosis. If the point is in between, then denotes either the compensations or mixed. So physicochemical approach is used to explain the causative mechanism of metabolic acid-base disorders. According to Stewart's theory of acid-base balance, variables like strong ion difference, PCO2 and AT2 reflects the plasma concentration of weak non-volatile acids, namely albumin phosphate. Bicarbonate ions are a marker of metabolic acid-base disorders and not its causative mechanism. So sodium and chloride are the main strong ion differences. So strong ion difference equal to sodium minus chloride. The difference that is decreased in metabolic acidosis is in metabolic alkalosis. So the concentration of dissociated non-volatile weak acids, anionic component 1 is albumin phosphate. The principal weak acid in plasma is albumin. So bicarbonate is a variable quantity not only in PCO2 but also by individual metabolic components. The strong ion gap denotes unmeasured ions. This is similar to the anion gap concept. So anion gap is equal to AT plus strong ion gap. So increased presence of unmeasured ions will not be clearly noticed. It will be masked. The concentration of dissociated weak acid is very low because the bicarbonate anion gap can be normal. So the anion gap has to be corrected for the serum albumin. So corrected anion gap is equal to anion gap plus 2.5 into 4.4 minus observed albumin gram per deciliter. So this is the relations strong ion difference, apparent strong ion difference minus ATOT plus strong ion gap is equal to bicarbonate. So in this equation, if you substitute the relation between standard bicarbonate and NRH plus, this will be getting the following relation: strong ion difference, apparent strong ion difference minus ATOT plus strong ion gap is equal to 960 divided by NRH plus into bicarbonate divided by standard bicarbonate. So from the above equation, very clear, the non-respiratory agent concentration is inversely proportional to strong ion difference, directly proportional to total concentration of dissociated weak acids, and directly proportional to the anion gap. And then delta gap is equal to sodium minus chloride minus 36, or main strong ion difference minus 36. This is directly proportional to the main strong ion difference. So this applied equation correlates the various parameters that helps to identify the hidden metabolic acid base disturbances and mixed acid base disturbances. So for practical convenience, main strong ion difference and the weak acid albumin concentration can be compared and correlated with the bicarbonate to find the causative mechanism of the metabolic acid base disturbances, because we are not estimating all the ions for practical purposes. So delta gap, the value is more than 6. It can denote either metabolic alkalosis or respiratory acidosis, because we discussed the previous slides. So strong ion difference and NRH plus are inversely related. So strong ion difference is increased in metabolic alkalosis, and NRH plus is decreased in metabolic alkalosis. Similarly, strong ion difference and the ratio between bicarbonate and standard bicarbonate are directly related. So this ratio is increased, the PCO is increased. So delta gap lesser than minus 6, it can be seen in non-anion gap metabolic acidosis, because the strong ion difference is decreased in metabolic acidosis, and the strong ion difference also decreased. The ratio between bicarbonate and standard bicarbonate is decreased. So this ratio is decreased if the PCO2 value is decreased. So this is seen in respiratory alkalosis. So delta gap, if the value is between from minus 6 to plus 6, it denotes only high anion gap metabolic acidosis. So I have shown 6 examples. In the first example, pH, PCO2 bicarbonate, all are same. But if you look at the sodium and chloride values, they are different. So sodium, in the first example 145 and chloride is 100. The second example, sodium is 140 and chloride is 105. If you see the difference between sodium and chloride, the difference is 45 in the first example and 35 in the second example. So sodium minus chloride, the strong ion difference is increased. If it is increased, then it can denote metabolic alkalosis. So if you look at only if you see the pH PCO2 bicarbonate, it will mislead us. So you have to look at the individual sodium and chloride values also. So in the third example, from third to sixth example, if you look at the albumin concentration, it is lowered. So if the albumin concentration is lowered, it has to be corrected, because anion gap is calculated. If the albumin level is low, then it has to be corrected. So the corrected anion gap is higher in other examples. So if you don't correct the anion gap for albumin, then it will mislead. So you will miss the anion gap metabolic acidosis. So from this relation, it is very clear. Easy to compare. So identify the hidden metabolic acid base disorders, because sometimes the strong ion differences, you can look at the equation strong ion difference minus ATOT plus strong ion gap is equal to bicarbonate. So bicarbonate can be normal, high or low depending on the changes in strong ion difference, ATOT and strong ion gap. Strong ion difference is very high, it denotes metabolic alkalosis. But if the anion gap is very high, it denotes metabolic acidosis. So both metabolic acidosis and metabolic alkalosis can be present, but the bicarbonate will be normal. Similarly, the anion gap will be normal if you don't correct it for albumin concentration, because anion gap is equal to strong ion gap plus ATOT. The ATOT denotes the concentration of weak acids, mainly albumin. So if the albumin concentration is very low, the unmeasured ions concentration, it will be missed. So it will be masked. So we have to correct it for the serum albumin concentration. So transition from conventional contemporary ABG interpretation. So first step 1 is you have to verify the consistency of the report. Step 1, check the pH and total change in pH, and we have to compare and correlate with the respiratory and non-respiratory change in pH. And step 3, location of acid base disorder in the 4-quadrant graphical tool. We can easily locate metabolic alkalosis in the positive side of x-axis, metabolic acidosis in the negative side of x-axis, and respiratory acidosis in the positive side of y-axis, and respiratory alkalosis in the negative side of y-axis. And then you have to apply the compensation rules Well, we have to check whether values are expected or unexpected. If it is expected, then it is due to compensation. Unexpected, then it denotes the presence of additional second acid-base disorders. Then you have to calculate the anion gap for metabolic acidosis, and you have to correct it for the albumin, changes in albumin concentration. And if the anion gap is very high, you have to calculate the delta gap, and then you have to correlate with the Stewart's acid-base parameters to identify the hidden metabolic acid-base disturbances. So finally, the ABG interpretation done with correlating with patient history and clinical conditions. So conclusion, ABG interpretation remains an arduous task. It remains has immense clinical value. By developing a mobile application operating software, ABG is itself a novel interpretation method, graphical to represent medicine tools to identify the hidden and mixed acid-based disorders can be integrated. So implementation of this 7 steps approach will help to overcome the arduous task of ABG interpretation, resulting in saving life of countless patients. And these are my references. So thank you for giving me this opportunity to present in this international conferences. Thank you.